Welcome to AP Chemistry at Hononegah High School. Today we'll be looking at Chapter 2, which deals with atoms, molecules, and ions. Like Chapter 1, it's a fundamental chapter. There are probably a number of questions that'll end up in the AP test related to this, but it's really core background information. The vast majority of this chapter you've already seen before. So most of what we're looking at here is going to be reinforcing and getting greater depth of ideas that you looked at last year. Now, with Chapter 2, there are a couple of movies I posted on school notes. So after you're done looking at the notes, there are a few short movies that get into things like a better description of what's happening with Thomson and the cathode ray experiments, Millikan's oil drop experiment, Rutherford's gold foil experiment, law of multiple proportions. I've posted a number of movies. They're not long, but they'll give you much greater depth and understanding and great visualizations of some of the ideas we've been talking about. So after you're done with the Chapter 2 notes, don't forget to watch the short Chapter 2 movies. You link to a website, and from there you can watch the movies that I've listed. There's a bunch of other movies you can watch if you want, but those are the ones that I really wanted for Chapter 2 for you to take a look at this time. Now, Chapter 2 starts out with atomic theory of matter. The theory that atoms are the fundamental building blocks of matter reemerged in the early 19th century, championed by John Dalton. You may remember from last year, Dalton's atomic theory. And for a long time, scientists had been mired in the idea that the world didn't exist as particles, that it existed in fundamentally very different ways. And that was really trying to uphold old bad theories, was really leading scientists down a lot of wrong paths. And once Dalton published his atomic theory, it really was the beginning of modern chemistry, a great look at really how the world does exist around us. And it was really the beginning of what we're looking at in class this year. What he basically said was each element is composed of extremely small particles called atoms. All atoms of a given element are identical to one another in mass and other properties, but the atoms of one element are different from the atoms of all other elements. Third, he said that atoms of an element are not changed into atoms of different elements by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. What happens to them is they're rearranged. Compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kinds of atoms. So water is made up of hydrogen and oxygen atoms, and it's always 2 hydrogen atoms to 1 oxygen atom. And these were Dalton's fundamental postulates that he presented to the scientific community that really got scientists thinking in the right way. Now, not all of these postulates are 100% accurate, but it really was a major paradigm shift in thinking and really got scientists and modern chemistry rolling. Now, which of these do we still believe are true? Well, all atoms of a given element are identical to one another in mass and other properties. We know that's not true. We have isotopes. The same element, carbon, but it can have different numbers of neutrons in its nucleus. So therefore its mass and other properties are going to be slightly different. Chemically, same number of protons and electrons, so chemically it's going to be the same, but not physically. Now, one of these postulates, postulate number 4, is also known as the law of definite proportions. The elemental composition of a pure substance never varies. So we say water is H2O, water is always H2O. Hydrogen peroxide would be H2O2. Hydrogen peroxide is always H2O2. And this is really kind of a common sense law. Fundamentally, it says that a molecular substance is always, or an ionic substance, is always made up of the same fundamental ratio of particles. Postulate 3, the total mass of a substance present at the end of a chemical process is the same as the mass of the substances before the process took place. That was a very important idea in chemistry because it really got rid of some very screwy ideas dealing with things like spontaneous generation and so forth. Once it could be quantifiably shown that if you didn't let particles escape, what you weighed before is what you weighed afterwards, it really solidified our understanding of particle chemistry and really got rid of a lot of very bizarre theories that were out there. Law of multiple proportions. If 2 elements A and B combine to form more than one compound, the masses of B that can combine with a given mass of A are in a ratio of small whole numbers. There's a movie I want you to watch related to this idea. Many scientists contributed to our understanding of atomic structure. Really, you should have a basic understanding of what they discovered and be able to summarize it. And these are the different people that we're looking at here. J.J. Thomson, the electron. There's a movie I want you to watch about that, and the cathode ray tubes. Millikan, mass of the electron. Another thing, there's a movie related to that. Henry Becquerel discovered radioactivity. Ernst Rutherford discovered the nucleus and eventually hypothesized the existence and later proven that there's this thing called the proton. And James Chadwick was the neutron. These are the fundamental people that you should understand the role they played in our modern understanding of the atom. Now first, the electron. Streams of negatively charged particles were found to be emitted from a cathode ray tube. So if you had this thing called a cathode ray, there was this mysterious beam of particles that was moving through this ray moving through this tube from one side to the other. Now, J.J. Thomson was credited with the discovery of the electron because what he was able to show was this mysterious beam that was moving across this tube was, one, electrically negative, and two, it had to be made up of electronegative particles because as the beam was running and these particles were moving across the screen, the mass over here was steadily increasing. So what was being added to this far screen had to be a particle. It had a mass and it also had a negative charge. And no matter what substance was in the cathode ray tube, the charge to mass ratio was the same. So if you calculated what the increase in mass was and you found what the increase in charge was, then you could find a ratio of the mass to charge, and we found out that that ratio was the same for every substance. So this negatively charged particle that was moving across this cathode ray tube had to be a fundamental particle in all substances, and he called that particle the electron. Now, one of the important things that came out of his work, and this is something that Millikan used a little bit later, was the charge to mass ratio, and he found that the electron had a charge to mass ratio of 1.76 times 10 to the 8th coulombs per gram. So if you had a gram of electrons being deposited on the far plate, it would have a charge of 1.76 times 10 to the 8th coulombs. And that was instrumental by Millikan in determining the mass of a single electron. So that's where we'll look next. Millikan's oil drop experiment was the method by which we were able to find and estimate the mass of an electron, and was actually calculated to very, very close to what we now believe the mass of an electron is. So for as simple as the apparatus was, it worked amazingly well. So once the charge to mass ratio was known, the determination of the charge or the mass of an electron would yield the other through dimensional analysis. So if we could calculate the charge of a single electron, and that was really Millikan's goal here, we could find the mass of that electron. And what he did fundamentally was he sprayed these particles in this upper chamber, little oil drops, and they would fall. And they would fall towards this positively charged plate. Now when they would move through this hole, when they would move through the electrical field generated by that positively charged plate through that little hole, the particles would pick up a negative charge. In other words, electrons were being stacked on them. And now when it came through, a random amount of electrons would be stacked onto that oil drop particle. And because it had a negative charge, if you had a negatively charged plate on the bottom here, you could increase the charge on that bottom plate until you could freeze that oil drop in space. Now granted, the heavier the oil drop was, that played a role in this. That was part of the difficulty in some of the calculations he made. But fundamentally, what he was able to do was determine for each individual oil drop what charge that oil drop had. And he was able to do this with thousands of calculations. So it was a very tedious type of experiment. And eventually what he was able to do was take his numbers, and he realized that all of them had to be multiples. All of the charges that he calculated had to be multiples of some fundamental charge, and that would be the charge of a single electron. So he was able to use the math to work backwards and calculate the charge on one electron. And if you use the charge to mass ratio, you could then calculate the mass of a single electron. So with the electron charge known, The charge mass ratio was used to determine the mass of a single electron. Next, radioactivity. Radioactivity is the spontaneous emission of radiation by an atom. And understanding radioactivity was not only very dangerous, but gave us lots of insight into what was happening inside atoms, and later we knew into the nucleus of atoms. So our understanding of radioactivity was really important in our understanding of the atom. It was first observed by a scientist by the name of Henry Becquerel. Now, Marie and Pierre Curie also studied it. And what they found was there are three types of radiation. Rutherford picked up their work into alpha particles and beta particles, and was able to determine that in the end, in radioactive processes, there seem to be these mysterious particles or energies coming out of unstable substances, and those unstable substances were radioactive substances. Sometimes the energy form or particle that was coming out was an alpha particle, so that was one type of particle that was determined. If you took that radioactive energy that was coming out of substances and you passed it through an electrical field, if it was positively charged, it would be deflected by the positive plate and attracted by the negative plate, and you would see a bending of that particle when it would hit this photographic plate at the far side. You could also use a phosphorescent screen and see where it's impacting the screen. And one thing they found out was that there was one type of particle that was coming out that was positively charged. They also found out that there was another type of particle that would be repelled by the negative plate, attracted to the positive plate, and it moved a much greater amount, which meant it was a significantly smaller particle. Those are beta particles. And then finally, gamma rays, those things weren't particles at all, and it did not have a charge. It was not deflected in either direction. So it was totally neutral to the positive and negative plate, and those would be your gamma rays. So there were three fundamental particles that were coming out of radioactive decay. Now, around 1900, our view of the atom looked essentially like this. The prevailing model, which really came from Thomson's work, was called the plum pudding model. And what you basically had was a positive charge spread over this sphere with negative electrons stuck to it. So they were stuck like pieces of raisin in this pudding. So that's why it was called the plum pudding model. Now, it featured a positive sphere of matter with negative electrons really embedded in it. Now, the first person to really fundamentally change that view of the atom was also Rutherford. Now, Rutherford was working with alpha particles, which he knew were positively charged. He was firing them at a thin sheet of gold foil, and he observed the pattern of scatter. Now, what he had felt and what other scientists had felt was there was a lot of empty space, so most particles would go straight through, which that was upheld, so most of the particles did go straight through. So that told them that inside an atom there was lots of empty space, and they figured they'd see some particles being deflected. What they weren't prepared for was the fact that some particles were bouncing straight off and coming back. And that was, as he described it, like shooting a howitzer or a sheet of paper and having the howitzer bounce off. An alpha particle is a relatively large charged particle. If it hits something, it should be just barely deflected because it should be much larger than what's inside the atom. If it actually bounces off and comes back, that must mean that all of that positive charge wasn't just dispersed throughout the sphere, but those must be particles inside there, and they must be concentrated in a very massive area that he called the nucleus. So since particles reflected at large angles, Thomson's model could not be correct. The positive charge had to be centrally located into a very, very small space. So most of the atom was empty space, but there was this very small dense nucleus, and the electrons then must be somewhere outside of that nucleus because the nucleus had to be positively charged. So most of the volume would be empty space. Now, protons were discovered by Rutherford around 1919. He had suspected the existence of them, but it wasn't until 1919 that we were able to point to any experimental data that showed that though that positive core inside there was made up of positively charged particles. Now, we couldn't really explain all of the mass of the atom yet, and that was because not only were there positively charged particles inside that nucleus, but there were also neutrally charged particles, which are very important in the stability of the atom, and those were the neutrons, and those weren't discovered until 1932 by James Chadwick. And that basically gave us our fundamental picture of the atom at that point. Now, the next section, 2.3, gets into our modern view of atomic structure. Protons and electrons, they're the only particles that have a charge. Protons and neutrons have essentially the same mass, and the mass of an electron is significantly smaller than the mass of protons and neutrons. So often when we're talking mass of atoms, we totally ignore the electron because they're like 2,000 times smaller than the protons and the neutrons. So their mass really isn't significant when you are looking at the mass of the overall atom. Symbols of elements. Well, elements are symbolized by 1, 2, or 3 letter. Most of them are 2 letter, but there are some very early atoms that were single letter, and there are some more modern radioactive elements that have been discovered that have been given 3 letter codes. But they're symbols that are 1, 2, or 3 letters. First letter is always capitalized. Remaining letters are always lowercase. All atoms of the same element have the same number of protons. That would be the atomic number, which is referred to as Z. So if you ever see a capital Z in chemistry, they're talking about the atomic number or the number of protons. And in this method for showing a specific type, that would be the number that's in the lower left-hand corner of the notation that's up above. And mass number would be the total number of protons and neutrons. In other words, the number of nuclear particles. To the 10th place, the mass of an atom is the atomic mass in atomic mass units. So if you know what the substance has as a mass number, to tenths you basically know the atomic mass of the atom. Because remember, electrons, even if there's quite a few of them, aren't really contributing much to the overall mass, at least to the 10th place. So mass number is how we describe basically a specific kind of carbon. So we use mass number when talking about isotopes. Isotopes are atoms of the same element with different masses, and they have different masses because they have different numbers of neutrons. All of these are forms of carbon that can exist. Now, they're all not stable, but they all are forms of carbon that can exist. Notice they all have the same atomic number, but they have different mass numbers, and that's because they have different numbers of neutrons. Now, another method to describe a specific isotope, besides the symbol notation you see here, is to use what is commonly referred to as hyphen notation, the substance, and then hyphen the mass number. So carbon 11, 12, 13, and 14. Now, at one time, the atomic mass unit was really based upon hydrogen. We've since moved on from that, but an atomic mass unit is now derived or based upon a carbon atom. And if you take a carbon-12 atom, which is our stable, normal form of carbon, and divide it by 12, you're in essence looking at the mass of 1 proton or neutron, because they're essentially the same. Not exactly, but essentially the same. So one atomic mass unit really has a actual mass of 1.66054 times 10 to the negative 24th grams. So it's a significantly small number. So when we're talking about masses of atoms, we usually use atomic mass units because it's much more convenient than talking about these small masses. Now, atomic and molecular masses can be measured with great accuracy by using a mass spectrophotometer. There is a section in the book I want you to make sure you look at closely, because we're just going to breeze through this. I want you to have a fundamental understanding of how a mass spectrometer works, because it's been instrumental in our understanding of atoms and in modern instrumentation in looking at substances. And basically what's happening in a mass spectrometer is you are passing a sample through an ionizing electron beam, which then moves it through a magnet, and based upon the deflection and where it hits the far screen, you can determine the masses of the particles that are coming out. So the difference in the particles can be determined by their deflection from the middle. Now, because in the real world we use large amounts of atoms and molecules, we use average masses in calculations, because we're never talking about just a couple of atoms, we're talking about massive batches of atoms. And it is true that the average mass of a large batch of atoms is relatively stable. So average atomic mass is what we typically use. And the average mass is really calculated from the isotopes of an element weighted by their relative abundances, because everything is going to contribute some to the overall average mass, but the ones that are more abundant are found more in the sample are going to contribute more. And this is a type of calculation that you did last year, so this should look familiar. Should be able to calculate the average atomic mass of a substance from their percent abundances and the mass of the isotope. So if you take the mass of the isotope times its percent abundance back as decimal, that will tell you how much that particular isotope contributes to the mass. Do that for all the isotopes and then sum them, and you'll get the average mass of the isotope. In particular, look closely at exercise 2.4 on page 47 to see an example of this calculation. So this is something you need to be able to do for the test over this material. Now 2.5, the periodic table. Dalton's atomic theory set the stage for experimentation about atoms and the search for new elemental particles. Because we knew that the world existed as these fundamental particles called atoms, understanding and finding all of the different types that existed in the world around us became very important. And these efforts culminated in the development of the first periodic table in 1869. So as we became to understand the atomic world better, and we realized the relationships between the different atoms, when Dalton put his first periodic table together, there were blanks in it. Those were mystery elements that we were looking for. So really, a periodic table is a systematic catalog of the elements. Elements are arranged in order of increasing atomic number. His first periodic table was by atomic mass, but Moseley changed that into atomic number, which is what our modern periodic table is arranged by. When one looks at the chemical properties of elements, you'll notice there's a repeating pattern of reactivity. So when you look at hydrogen, helium, lithium, beryllium, and so on, there is a periodic repetition in behaviors. So you end up with substances that have similar chemical and physical properties being arranged in a column on the periodic table. And that's really what the periodicity part of periodic table means, a periodic repetition of properties. Now the rows on the periodic chart are called periods, and the columns are called groups. Now elements in the same groups have similar chemical properties to each other. And because of that similarity, and this is not all of the elements in all of the columns on the periodic table, but a number of them are very, very, very similar to each other. And they ended up getting their own names. So group 1 on the periodic table, minus the hydrogen, lithium, sodium, potassium, every one of these things is very, very chemically similar to each other. So similar that they gave them a family name. So groups or families are what the columns are on the periodic table. But the ones that are common enough that you will see throughout the year: alkali metals, 1A, alkaline earth metals are the 2A, halogens are the 7A, noble gas are the 8A. Those 4 are very, very common. 6A is called the chalcogens. That would be the family that starts with oxygen. So that's one that you're moving across the stair steps, so it's not as repetitive in terms of its properties. It does have a name, but you'll rarely see that one. Usually you would call that, just by the head of the family, the oxygen family. So to the left of the oxygen family, you'd have the nitrogen family. But those 4, 1A, 2A, 7A, and 8A, all have names that you should know by their family names. And the others are often referred to by the element in the top. And like I said, chalcogens, that's probably one that you won't see, but that would be the oxygen family. Now, nonmetals are on the right side of the periodic table with the exception of hydrogen. So hydrogen plus that upper right-hand corner are substances that are non-metallic in behavior and properties. Now, along the stair steps that you see on most periodic tables, you should remember this from last year, minus really the aluminum, and polonium and astatine are also not usually put in this group, but it depends upon the book, so think of it as really minus aluminum. Things that are above and below the stair steps minus aluminum are your metalloids. They have properties indeterminate. In other words, they sometimes act like metals and sometimes act like nonmetals. Everything else in the periodic table would then be metals. So the vast majority of our substances are metallic substances. And later in the year, we'll be getting much deeper into what those things mean. Now, even though the atom is the smallest sample of a substance, only noble gas elements are normally found in nature as stable atoms. And you should remember from last year the whole octet rule thing and the full outer shell, why they have stability, but that's for a future chapter. Most substances in nature exist as molecules, two or more atoms bonded together as a neutral unit. And this is using the general term of molecule. In specific molecular terms, that's when we're talking about our non-metal combinations. If you have a metal and a non-metal, then typically what we have is a situation where electrons have been transferred. You get oppositely charged particles that stick together to make a neutral unit. Those are our ionic compounds made up of formula units. But here we're looking at just the generic term of molecule, being a group of atoms bonded together. After this, we pretty much always talk about molecular as these things. Nonmetals covalently bonded together to make a fundamental unit that can be picked up and looked at, and then that fundamental unit has properties that are constant throughout. Now, the subscript to the right of the symbol of an element tells the number of atoms of that element in one molecule of the compound. So your subscript describes how many of that particular element. And molecular compounds are composed of molecules and almost always contain only nonmetals. Here we're looking at the specific idea of this fundamental particle, the molecule. So we have atoms, we have molecules, and then we also have formula units for ionic compounds. Now, there are 7 elemental substances that just aren't stable enough to exist as elemental substance, but they'll readily get together and share electrons to form a molecular unit. These are the diatomic molecules. You need to know them. You need to know them extremely, extremely well. When I say oxygen, you need to understand I'm talking about O2. Unless I say oxygen atoms, I always mean O2 when I refer to oxygen. So the Han-Fickelbrei, the hydrogen 7. So hydrogen, go to number 7, make a 7. Or genuine, all the ones that end in gen or ine. Those are going to be your diatomic substances on the periodic table. Empirical formulas give the lowest whole number ratio of atoms of each type of element in a compound. So HO would be an example of an empirical formula. It's the lowest whole number ratio of hydrogen to oxygen here. That does not mean that there is a substance that is HO. That may or may not be the case, but an empirical formula would be the lowest whole number ratio of the atoms in a compound. Now, molecular formulas give the exact number of atoms of each element in the compound. So something like hydrogen peroxide would be H2O2. That's the molecular unit that gets formed. Oxygens bonded together with a hydrogen on each oxygen. And that makes this distinctive unit called the H2O2 molecule, hydrogen peroxide. Now, that is not the lowest whole number ratio. If you reduced it, you would get HO. So remember, the empirical formula is not always the same. It can be, but in the case of hydrogen peroxide and many other things, the empirical formula is not the same as the molecular formula. But from experimental data, you should really be able to calculate and determine both of these. Now, types of formulas. One way of describing a formula is to use what's called the structural formula. And it really helps us see how the atom is bonded together. So this would be our structural formula. You're going to use that very, very, very often in chemistry. Now, a form of the structural formula is called the perspective drawing, which is the second one listed here. You'll sometimes see this in books because it brings three-dimensional imaging. You can see the dotted line hydrogen farther away. The broad line means as it's getting closer to you, the line broadens, so that hydrogen is closer to you. So the perspective drawing helps you see a two-dimensional image as a three-dimensional object. Another common use is the ball and stick model. When you've built molecular substances before, you were making, ball and stick models. Well, taking a picture of that 3D object in 2 dimensions, you get a ball and stick model. It also is a visual way of representing, and it's really closer than the structural formula into seeing what it really looks like. But it's really a representation. A better way to show what it really looks like is to use the space filling model, which you're going to see this year a lot more than you saw last year, because it really shows the respective spheres of influences of the different atoms and how they're bonded together, and it really shows the space of the molecule. So what is the sphere of influence of the electrons in the different substances as they're buzzing around the atoms that are covalently bonded together? Space filling model does a much better way of representing that than the others. Now, besides forming molecules, some atoms or group of atoms can gain or lose electrons to form ions to become stable. And here's where we're going to get into our ionic compounds and our formula units. When atoms lose or gain electrons, they're becoming stable in a different way than when they're sharing electrons like molecules do. And they become what we call ions. Positive or negatively charged particles that have gained or lost electrons to become stable. Cations are positive. You know it's positive because it's got that T, which looks like the plus sign in the middle of it. So remember, that's a clue that the cations are the positive ones. And they're formed by elements typically on the left side of the periodic table. They are metals. Metals are fundamentally things that it's easier for them to lose electrons to become stable. That's what makes a metal a metal. And not all metals lose electrons as easily. So we're going to talk about later which metals behave more metallically. Anions, on the other hand, are things that gain electrons to become stable, and those are typically your nonmetals. Your things in the upper right portion of the periodic table tend to do that. Now, monatomic ion charges can often be predicted by where they're at in the periodic table. So remember, cations and anions are gaining or losing electrons to become stable. Well, if the noble gases have the magic number of electrons, then things in this column would be 1 away from a noble gas. So when they gain 1 electron, they would become stable. These are 2 away, that's 1 away. On the flip side, your cations, they're losing. So these all lose 1 to be a noble gas. These would lose 2, something like aluminum would lose 3, and so on. So based upon where it's in the periodic table, you can often, for a single atom ion, determine what its charge is going to be. Now when you get into the transition elements, it becomes a little bit more complicated, but we'll be getting into that later in the year. Now ionic compounds, such as sodium chloride, are generally formed between metals and nonmetals, things that gain and things that lose electrons, and those are typically metals and nonmetals that are doing that. And what they end up doing is transferring electrons between the two so they both become stable, and now they're oppositely charged. Opposites attract. So how do you tell compounds apart? Well, remember, ionic compounds, and this is a fundamentally important idea, which was important last year, and you should all know this, but you need to remember it. Ionic compounds are usually combinations of metals and nonmetals. The one exception to that would be ammonium, which is NH4+. Notice it's a group of atoms with a charge. There's no metal in there, but yet this thing is still an ion. Molecular compounds are generally composed of nonmetals. They are non-metallic elements that really none of the elements are strong enough to steal electrons from others, so what they end up doing is sharing electrons between the two. Now, because compounds are electrically neutral, you can determine the formula of a compound in this way. Remember this from last year? We always called it crisscross reduce. So if you've got an ionic compound, the electron transfer needs to be equal, and that demands a very specific number of cations and anions together. And you can use charge to determine what that number is. So the charge of the cation becomes the subscript on the anion, and vice versa. So that's why we call it crisscross. And then you have to remember that the fundamental formula unit of an ionic compound is the smallest number of cations and anions, so you have to crisscross and then reduce. So if these subscripts are not the lowest whole number ratio, divide to get the greatest common factor. Now, here is a list of, some common cations. You'll notice most of these on this list are monatomic, with the exception of ammonium NH4, NH4 plus, I should say. But these are all substances that you're going to routinely see throughout the course of the year. Notice some substances can have multiple charge state, and in modern naming, we use Roman numerals to show what the charge is. So copper 2 versus copper 1. The old way of saying that would be Us is the lower charge state, Ik is the higher charge state. So you had copper or cuprous, and now we just call it copper 1. It's significantly easier. But should at least be familiar with that idea that Us is the lower charge state and Ik is the higher charge state when you have multiple charge states. Now, common anions, here you do notice also that there's a lot of monatomics, but now we start to see a lot of polyatomics, group of atoms that have gained or lost electrons, and you need to be familiar with these. Remember, test on day 2 of the year is going to be testing those common polyatomic ion names and formulas, as well as a few monatomics. Be prepared for that. Now, nomenclature is our system used to name substances, and there's 2 major categories in nomenclature. Organic compounds, which are carbon-containing molecules that have at least 1 hydrogen stuck to the carbon, and we're going to talk briefly about this in 2.9. This is the only thing in all of these first 3 chapters that's actually going to be new. Everything else is going to be a repeat from last year. And then back in 25, we're going to get some more. So once we get a little bit later in the year, we're actually going to do chapter 25. That'll come in first semester, but not yet. So organic compounds are one type of category, and we name them very differently than we name inorganic compounds. So inorganic are really all the other compounds. Now, naming inorganic compounds, you're going to write the name of the cation, because what we're looking at here is typically ionic compounds. You're going to write the name of the cation first. If the cation can have more than one possible charge, remember, write the charges Roman numerals in parentheses. And then second, you're going to list the anion. And if it's a monatomic, it's going to get changed to an "ide" ending. If the atom is polyatomic, you're going to simply write the name of the polyatomic ion. Now, there is rhyme and reason to why you get other types of naming, like eights and ites and so forth. And that's something that we will be getting into when we talk about acids, because you'll see a little bit more relevant to those different types of endings there. But for the most part, if you've memorized them, all you really have to do is write what it's called. So if you see SO4, that's called sulfate. If you see SO3, that's called sulfite. You need to know the difference between the two. Now, when there are two different oxyanions involving the same element, and I just talked about sulfate, sulfite, so something like nitrite and sulfite, the one with fewer oxygens gets the "ite" ending. The one with more oxygens gets the "ate" ending. So NO3 minus is nitrate, but NO2 minus was nitrite. SO4 2 minus was sulfate, but SO3 2 minus was sulfite. So that's really where the ite comes in. But there are substances that can actually have even less and even more oxygens than what we listed here. So this ite family of oxyanions is a little bit bigger than just ites and eights. An example of that would be our chlorine oxyanions. You can have chlorite, which has 2, and it's got a charge of -1. So then chlorate would be 1 more, ClO3 minus. But besides the ite, you can have even less oxygens than 2 and still form a stable substance here. And you can have even more than 3 and still form a stable substance. So really our family is broadened just a little bit. The one with fewer than the ite is called the hypoite. So chlorite would be ClO2 minus, hypochlorite would be ClO1 minus. And the one with more oxygens than the 8 is per-8. So perchlorate would be ClO4 minus, because chlorate was ClO3 minus. So there are some different substances like the halogens with oxygens that can form these 4 family groups of polyatomic oxyanions. Now, acid nomenclature is really based upon the anion. So when you're looking at acids, remember acids are an anion with a ionizable hydrogen on it. And what the anion has as a name is used to determine what the name of the acid is going to be. So if the anion in the acid ended in "ide," you're going to change the ending to "ic" acid and add the prefix hydro. So HCl comes from chloride, so that becomes hydrochloric. HBr comes from bromide, hydrobromic. HI comes from iodide, hydroiodic. So if it was an "ide" ending, you just put in hydro and ic. If it's an ite ending, then, and remember, this actually goes back to old naming here. Cuprous was the lower charge state one. So when you have the lower oxygen situation, the ite, then you get the us name as an acid. So HClO would be hypochlorous acid because it came from the hydroite. So now it becomes hypoite. So now it becomes the hypo-us. Whereas chlorite was just chlorite. Remember, ite becomes us here. So chlorite becomes chlorous acid. So the lower charge one is us, just like I'd mentioned with copper 1 and copper 2. The higher charge one, ate becomes ic. So if you had chlorate, which is HClO3, that's got hydrogen in a chlorate, that becomes chloric acid. And once again, remember we can have perchlorate. So if we have HClO4, the 8 still becomes ic, but we still have the per there. So perchloric acid would be HClO4. Perchloric acid and chloric acid are 2 of our strong acids that you're supposed to know. The less electronegative atom is always listed first in binary compounds. So electronegativity plays a role in this. So when you have water, there's a reason why it's H2O and it's not OH2. because you always list the least electronegative first, and that's something we might not have talked about in pre-AP. Now, a prefix is used to denote the number of atoms of each element in the compound. Mono would be 1, but by notation we don't use mono on the first element. Now, the ending on the more electronegative element is changed to "ide." So the second one listed would become an "ide." So we have carbon. Remember, you don't put mono on the first one, and you leave the name alone. And the second one, you change the ending to "ide." Well, there's 2 oxygens, so it would be dioxygen, but the oxygen becomes oxide, so carbon dioxide. CCl4, still carbon. Remember, technically it's monocarbon, but we don't say the mono, and we don't change the ending on that element. But in the second one, we change its ending, and we use the prefix to describe how many. In this case, 4 would be tetra, so carbon tetrachloride. Now, the prefix, if the prefix ends with an A or an O, it ends up with a goofy to pronounce substance. And when that happens, so when you get these 2 successive vowels, you basically drop the one vowel and blend it into one. So dinitrogen pentoxide, pentaoxide can be somewhat odd to say, so you drop the A. So if you have an A or an O and it's being linked with an element that starts with a vowel, then you drop the prefix. But that's only for A's or O's. So tri, that still stays, trioxygen. Now at this point we're only looking at simple organic nomenclature. And that will let us understand some of the organic compounds we're going to encounter before we get to chapter 25. So this is the one thing that's new. So this is something that it's one of the reasons it's really important to watch these notes is so that you pick up on some of the new stuff. Well, in these first 3 chapters, this is pretty much it. There are going to be some substances that we're going to encounter from time to time before we get to chapter 25, and you just need to understand them. So we're going to get into a little bit of simple organic here. What you really need to be able to do is count to 10 in organic. Organic chemistry is the study of carbon compounds. Remember, technically it was carbon with at least 1 hydrogen attached to it. So it's not true technically to say it's the study of carbon compounds, but you understand what we mean when we say carbon compounds. Notice all of these have a hydrogen, at least 1 hydrogen stuck to one of the carbons. Now, organic chemistry has its own system of nomenclature, which gets very complex. So we're going to deal with this at its simplest level. The simplest hydrocarbons, which would be compounds containing only single bonded carbons and hydrogens, are called alkanes. Notice all of the carbons have single bonds. If you saw any double bonds, it would not be an alkane. So we're talking about simple single bonded carbon substances here. Each carbon is always going to be then bonded to 4 other things. If you can't have double or triple bonds, every carbon is going to be bonded to 4 other atoms. A name for this is they're called saturated substances. When it's full of bonds, carbon full would be 4 bonds, that would make a saturated alkane. So the term saturated versus unsaturated is really talking about whether you have all single bonds or whether you got some double bonds in there, adding a little chemistry on the side there. So each carbon atom is basically full of bonds here, which would be 4, all single bonds. Now the first part of the name above corresponds to the number of carbons. I said you need to be able to count to 10 in organic. Meth is 1, eth is 2, prop is 3, bute is 4, pent is 5, and so on. So if we have methane, that means 1 carbon. Ethane, that means 2 carbons. Propane means 3 carbons. And the ane part means we have an alkane. They're all single bonds. So counting to 10 in carbon, you have to be able to do this, and this is the one thing that's new. And really notice these are the same as the binary molecular substances we look at, so really it's only the first 4, meth, eth, prop, bute. All the rest of them are the exact same as what we looked at with molecular substances, and that makes this significantly easier. So it's really, remember, 1 through 4, meth, eth, prop, bute. Now, one form of an alkane, this is a substituted alkane, we have a different group on than all hydrogens, is the alcohol group. The alcohol group is real important, and because we're going to run into it from time to time, you need to be at least fundamentally aware of it now. So we have alkanes, and you need to be able to talk about the first 1 through 10 carbon alkanes and what their names are. And then we have when we put this OH group on. Now, it's called a functional group because when we substitute one of the hydrogens with an OH, it changes the function of the molecule. It behaves different. So adding the OH functional group is what makes an alcohol. So if we have a hydrogen and alkane replaced with something else, another functional group like an OA, it's going to change how we name that alkane. And the only one we're going to really look at here is going to be the alcohol group. So the ending denotes that this type of compound for alcohols would be OL, all. So you change the ending at the end to contain an OL on it. And different functional groups substituted on would have different endings. We're just not getting into any of them at this point. We're barely going to touch on to a few later on. But at this point, I want you to be able to know the first 10 hydrocarbons. And if we stick a hydroxyl group on there, an OH group, that it makes it an alcohol, and that changes the name a little bit. So if we put it onto our methane, we get methanol. If we put it onto our ethane, we get ethanol. Now, notice when we put it onto our propane, we get propanol. But because there's different places that could go on, in the first one here, no matter where I stuck it, it's on the first carbon. So I don't need to tell where it is. No matter where I stuck it here, it's on an N carbon, a first carbon in the chain. So I don't need to say where it is. But when I have 3 carbons in a row or more, I have to tell you where that alcohol group is in the structure. So in this case, it's on the first carbon. You always start your numbering where your functional group is going to be on the lowest number. So I wouldn't number it 1, 2, 3. Because the OH is over here, I'm going to get rid of that idea, and I'm going to start numbering at 1, 2, 3. So it's a propane group, and since it's on my first carbon, then we call it 1-propanol. If it was here, then it would be 2-propanol. Now, if it was here, it's not 3-propanol. That's still 1-propanol, because then my chain would be numbered the other way. If I had it in this position, it's back to on the first one. So that would also be 1-propanol, because we can just take this molecule and flip it and be the exact same thing. So it's not a new substance if I stick it on that other N carbon. And that ends the notes over Chapter 2. Don't forget to watch the Chapter 2 movies.